Inductance, AC resistance. In electromagnetism and electronics, inductance is the property of a conductor by which a change in current flowing through it creates a voltage, electromotive force, in both the conductor itself, self-inductance, and in any nearby conductors, mutual inductance. Generators. In electricity generation, an electric generator is a device that converts mechanical energy to electrical energy. It follows a right-hand rule, where the thumb represents motion of the conductor, the first finger the magnetic field, and the second finger the current flow. The force generated is known as the Lorentz force. The magnetic force component of the Lorentz force is responsible for motional electromotive force, the phenomenon underlying many electrical generators. When a conductor is moved through a magnetic field, the magnetic force tries to push electrons through the wire, and this creates the electromotive force. The term motional EMF is applied to this phenomenon, since the EMF is due to the motion of the wire. When the conductor is vertical, no current flows. As it rotates to a horizontal position, current flows. This current decreases as it returns to vertical again, and so on, forming an oscillating sinusoidal alternating current and induced voltage. The current is transferred to slip rings through which the wire, armature conductor, is free to rotate. A generator contains stationary and rotating components. A commutator produces DC. To make the generator output DC, slip rings are replaced with a commutator. Generators. In 1827, Hungarian Ányos Jedlik started experimenting with electromagnetic rotating devices, which he called electromagnetic self-rotors. In the prototype of the single-pole electric starter, finished between 1852 and 1854, both the stationary and the revolving parts were electromagnetic. He formulated the concept of the dynamo at least 6 years before Siemens and Wheatstone, but didn't patent it, as he thought he wasn't the first to realise this. In essence, the concept is that instead of permanent magnets, two electromagnets opposite to each other induce the magnetic field around the rotor. It was the discovery of the principle of self-excitation. Jedlik's invention was decades ahead of its time. In the years of 1831 to 1832, Michael Faraday discovered the operating principle of electromagnetic generators. The principle, later called Faraday's law, is that a potential difference is generated between the ends of an electrical conductor that moves perpendicular to a magnetic field. Experimenters found that using multiple turns of wire in a coil could produce higher, more useful voltages. Since the output voltage is proportional to the number of turns, generators could be easily designed to produce any desired voltage by varying the number of turns. Wire windings became a basic feature of all subsequent generator designs. Dynamos, DC generators. The dynamo was the first electrical generator capable of delivering power for industry. The dynamo uses electromagnetic principles to convert mechanical rotation into a pulsing direct electric current through the use of a commutator. A dynamo consists of a stator, which provides a constant magnetic field, and a set of rotating windings which turn within that field. The constant magnetic field may be provided by one or more permanent magnets. On larger machines, the constant magnetic field is provided by electromagnets, known as field coils. The output of the generator can then be varied by altering the current in the exciter field coils. Without a commutator, the dynamo is an example of an alternator, which is a synchronous singly fed generator. With a commutator, the dynamo is a classic direct current generator. The alternator must always operate at a constant speed that is precisely synchronized to the electrical frequency of the power grid for non-destructive operation. The DC generator can operate at any speed within mechanical limits, but always outputs a direct current waveform. The essential difference between aircraft AC alternators and DC generators, dynamos, is that the induced output windings of the alternators are fixed, stator, and the dynamos have a fixed inductor, field coil. DC and AC generator summary. A dynamo produces DC, has a commutator, the rotor has the high voltage, and the stator has low voltage to the field windings. The alternator produces AC, uses slip rings, the rotor has low voltage to the field windings, and high voltage to the stator. Parts of a generator. The two main parts of a generator or motor can be described in either mechanical or electrical terms. For mechanical, the rotor is the rotating part of an electrical machine. The stator is the stationary part of an electrical machine. For electrical, the armature is the power-producing component of an electrical machine. In a generator alternator or dynamo, the armature windings generate the electrical current. The armature can be on either the rotor or the stator. The field is the magnetic field component of an electrical machine. The magnetic field of the dynamo or alternator can be provided by either electromagnets or permanent magnets mounted on either the rotor or the stator. Because power transferred into the field circuit is much less than in the armature circuit, AC generators nearly always have the field winding on the rotor, and the stator as the armature winding. Only a small amount of field current must be transferred to the moving rotor using slip rings. Direct current machines necessarily have the commutator on the rotating shaft, so the armature winding is on the rotor of the machine. An electric generator or electric motor that uses field coils rather than permanent magnets will require a current flow to be present in the field coils for the device to be able to work. If the field coils are not powered, the rotor in a generator can spin without producing any usable electrical energy, while the rotor of a motor may not spin at all. Very large power station generators often utilize a separate smaller generator to excite the field coils of the larger. Feeder. A feeder is the wire or buzz bar connecting a load with a generator. A feeder may short circuit, leak to earth or other phase, or open circuit. The disconnected wire becomes known as a feeder fault. A feeder fault on a direct current circuit could result from a flux imbalance between the voltage coil and the series winding turn. Series shunt wound generators. There are different ways of arranging the wires in a generator. Series wound field is in series with the armature. Load current increases with voltage. Shunt wound is essentially parallel. Field is parallel to the armature. And load current decreases with voltage. A combination of the two is known as compound wound, and load current is constant with voltage. The shunt wound generator. The shunt wound parallel generator has certain conditions to be met for activation. These are the presence of a permanent field and a minimum rotation speed. Diodes. A diode is a semiconductor device having high resistance in one direction and low resistance in the other. It's the hydraulic equivalent to a non-return valve. In this diagram, the horizontal x-axis is voltage, and the vertical y-axis is current flow. Between minus 100 volts to 0.5 volts, current flow is limited. Zener Diodes. A Zener diode is a special kind of diode which allows current to flow in the forward direction in the same manner as an ideal diode, but will also permit it to flow in the reverse direction when the voltage is above a certain value, known as the breakdown voltage. The device was named after Clarence Zener, who discovered this electrical property. They're typically used for voltage stabilization. Voltage regulators. Here is a voltage regulator comprising a stack of carbon discs, pressed by a spring to reduce resistance and pulled apart by the magnetic force exerted by the volts coil to increase resistance. The pile is in series with the shunt field, and an equalizing coil is available for parallel operations. If generator voltage increases, EMF increases, and the volts coil effect overrides the spring, so that the carbon pile relaxes. This increases the carbon pile resistance. Less current flows through the shunt field, and the EMF reduces until the forces exerted by the volts coil and the spring are equal. The voltage regulator of a DC generator is connected in series with the armature. Transformer rectifier units. A transformer rectifier unit is used on large power systems where frequency-wild AC generators, called alternators, are fitted to DC aircraft. Power. Because of the effect of Lenz's law at the load, some of the generated power, called reactive power, is used to drive current through reactances. So an alternator must be able to generate power in excess of the true power to do useful work. This power is the sum of true power and reactive power, and is called apparent power. Apparent power equals true power plus reactive power. To ensure correct load sharing between AC generators operating parallel, both real, true, and reactive loads must be balanced. Direct current generators are connected in parallel to provide maximum power. Generator breakers. Here's a diagram of a two-engined aircraft. The engine, which is rotating, interacts through a constant speed drive unit to turn the shaft of the generator, which has field windings where an exciter breaker exists. Thereafter, there's a generator breaker before connection to busbar 1. The same thing is paralleled for the second engine, connecting to busbar 2, and a tie breaker connects busbar 1 and busbar 2. So a certain service takes input from both systems, so the service will not entirely fail in the event of a single generator failure. So, for generators, which breakers open? Under the condition of an underspeed fault on an AC generator, the generator breaker opens. It's bad electricity. Persistent overexcitation, overvoltage on an AC generator connected to AC bus bars. It's bad electricity, so the generator breaker opens. Because there's been mention of excitation or overvolting, the exciter breaker opens too. A persistent top excitation limit fault on an AC generator connected to mains with another AC generator. It's bad electricity, so the generator breaker opens. There's mention of excitation, so the exciter breaker opens. But because it's connected to mains with another AC generator, it's isolated from it with the tie breaker opening too. Here's a sample electrical system for a 4-engined aircraft. The engines are connected to constant speed drive units or integrated drive generators, which connect to the shaft of the generator, which is connected to the AC bus bar, and then various synchronizing bus bars. AC generators. When the AC generators are connected in parallel, the reactive loads are balanced by means of the energizing current. The changeover relay allows power supply to the faulty AC generator's busbar if the generators are not paralleled. The fire shutoff handle causes a number of devices to disconnect in an AC generator. The exciter control relay and the generator breaker open, but the tie breaker does not necessarily open. Generator frequency. In order to produce an alternating voltage of 400 Hz, the number of pairs of poles required in an AC generator running at 6,000 RPM is. Well, the formula to calculate this is frequency equals synchronous speed multiplied by the number of pole pairs divided by 60. The generator was running at 6,000 RPM, So that's 6,000, multiplied by 4 pole pairs, divided by 60, producing a frequency of 400 Hz. Three-phase AC. Three-phase electric power is a common method of alternating current electrical power generation, transmission and distribution. A three-phase system is usually more economical than an equivalent single-phase system at the same voltage, because it uses less conductor material to transmit electrical power. The three-phase system was independently invented by Galileo Ferraris, Mikhail Dolivo-Dorovsky, and Nikola Tesla in the late 1880s. Single-phase loads may be connected to a three-phase system in two ways. Load may be connected across any two phases, or a load can be connected from phase to neutral, if neutral is available. Frequency-wild generators. The speed of a frequency-wild generator varies with engine speed. If you want to parallel three-phase AC generators, the following must be the same. Voltage, frequency, phase, and the voltage must be of the same phase.